All right, let's just jump right in. When you picture aliens, you're probably thinking about their spaceships or maybe their little green men, right? But what if the most alien thing about them isn't what they look like, but what they're actually made of? That is the absolutely mind-bending question we're getting into today, the search for life that breaks all the rules we know.
It seems like a simple question. Is all life made of the same basic stuff? Here on Earth, every single living thing, from a giant redwood tree to the bacteria in your gut, is built from the same chemical toolkit. And the star player in that kit is carbon. But is that the only way to build life in this massive universe? Or are we just being a little short-sighted, looking at everything through carbon-colored glasses?
Well, there's actually a name for that bias in the scientific community. It's called carbon chauvinism. It's this very human assumption that because our kind of life works so well here, it must be the standard for everywhere else. And for a long time, that idea has really guided our search for aliens. But now, scientists are starting to push past that, asking, okay, what else could be out there? What kind of stranger possibilities are we missing? So, to really appreciate just how weird life could possibly get, we first have to understand why carbon is the undisputed champion here at home. Let's break down why it's considered the absolute gold standard for biology.
The best way to think about carbon is like it's the master Lego brick of life. I mean, it is perfectly suited for the job. For one, it can form count 'em, four incredibly strong and stable bonds all at once. That lets it build these long, complicated chains and rings and all the 3D structures that make up things like our DNA and proteins. And here's the kicker. Its main waste product, carbon dioxide, is a gas. That means we can get rid of it super easily just by breathing out. It's hard to find another element that can match that kind of flexibility.
Okay, so if carbon is the champ, who's the #1 contender? Well, if you're a sci-fi fan, you probably already know the answer. Let's talk about silicon. The sci-fi dream of silicon-based life is just so cool, isn't it? You can just picture it, these slow-moving rock-like creatures or these majestic crystalline beings. And on paper, it makes a ton of sense. Silicon is right below carbon on the periodic table, so it has some similar properties, and it's the second most common element in the crust of planets like Earth. It really seems like the perfect candidate. But then we run smack into the hard reality of chemistry, and that's where the dream hits a snag. For starters, silicon-to-silicon bonds are just weaker than carbons, which makes building big, complex molecules really tricky. And then there's the waste product. When silicon burns for energy, it creates silicon dioxide, which is a solid. It's basically sand. Just imagine trying to breathe out tiny rocks. Not great. And to top it off, some silicon compounds are literally explosive when they touch water. So yeah, on an Earth-like world, silicon-based life would have a really, really bad day. So, the bottom line is this. The science just doesn't really back up the fiction, at least not in any environment we can easily imagine. Now, could it work in some truly bizarre, extreme place? Maybe. Think a world with scorching hot temperatures or one with rivers of something other than water. But for now, the chemistry is a huge barrier. Now, this isn't all just theory. Scientists have been actively looking for life that breaks the chemical rules right here on Earth. And that brings us to a really fascinating and kind of cautionary story from the real world that involves a very famous poison, arsenic. This whole thing was a huge deal. Back in 2010, the science world was totally electrified. NASA held a press conference announcing this bacterium called GFJ1 that seemed to do the impossible. It appeared to swap out phosphorus, an element essential for DNA, with toxic arsenic. If that was true, it would literally redefine life as we know it. But, science is all about checking your work. And by 2012, other scientists just couldn't get the same results. So the verdict today? The bacterium is an amazing survivor that can put up with a lot of arsenic, but it doesn't actually build it into its DNA. The claim was debunked. And the lesson from that is pretty profound. It just goes to show how incredibly difficult it is to swap out even one of life's core ingredients. The chemical bonds that arsenic forms just aren't stable enough in water. They fall apart way too easily. Chemistry has really strict rules, and so far, it seems every living thing on Earth plays by them.
Okay, so silicon is a long shot and arsenic was a bust. But what if we change the entire playing field? What if, instead of swapping the building blocks, we swap the liquid that life lives in? Let's take a quick, wild tour to the frontiers of biochemistry. First stop, imagine a freezing cold moon way out in the solar system. It's so cold that water is as hard as granite.
But here, you might find rivers and lakes of liquid ammonia, which could act as the solvent for a whole new kind of biology. Next, let's crank up the heat. Picture life floating in the acidic clouds of Venus or thriving near deep-sea volcanic vents. These organisms might not use oxygen for energy at all. Instead, they could be powered by bizarre chemical reactions based on sulfur. And for our last stop, and maybe the most mind-bending one, let's go to Saturn's moon, Titan. This is a world that's unbelievably cold. Its mountains are made of water ice, and its lakes are filled with liquid natural gas, methane and ethane. The big question is, could something actually be swimming in those cryogenic lakes? It's one of the most exciting mysteries in science today. Look, this journey through bizarre, exotic worlds is way more than just a fun thought experiment. This kind of thinking is fundamentally changing how we actually search for life out there in the cosmos. So, why does all this matter? Well, for one, it forces us to expand our whole definition of what life even is. It also sharpens our search for what we call biosignatures, the chemical fingerprints of life. So instead of just looking for oxygen in a planet's atmosphere, maybe we should be looking for weird combinations of ammonia or sulfur. And this thinking directly informs which planets and moons we decide to send our multi-billion-dollar probes to. And this isn't some far-off future plan. The search is happening as we speak. We are actively looking for life in the hidden oceans of Jupiter's moon Europa and Saturn's moon Enceladus. We are studying the methane lakes of Titan. And the James Webb Space Telescope is right now staring at the atmospheres of distant planets, hunting for any chemical sign of biology, whether it looks like ours or not. I think this quote just perfectly captures the two huge possibilities that drive this whole field of science. When we finally find life out there, we're going to learn one of two things. Either the universe is bursting with an incredible diversity of life, stranger than we can even dream of, or the specific set of conditions that created us here on Earth are unbelievably, beautifully rare. So that's the ultimate question we're left with, isn't it? As we look out into the stars, are we looking for life that followed the same chemical blueprint as us? Or are we the result of a beautiful, complex accident, a chemical masterpiece that may never have happened anywhere else? The only way we're ever going to find out is to just keep looking.
If you enjoyed this deep dive into the chemistry of the cosmos, let us know in the comments. Do you think silicon life is out there? Don't forget to like this video, subscribe to Lifelong Learners Hub for more fascinating explorations, and share this video with your friends to help us grow our community of curious minds.